And we move to the last presentation of this morning session. The presenter is going to be Juan, Esteban, Agudelo, Ortiz. And the presentation title is Deep Learning Techniques Implementation for the Generation of Stokes Parameters and Atmospheric Parameters in the Solar Context. I'm going to give you a 5-minute warning. Okay?
Yeah, thank you.
Here. So you can advance slides with this and get back with that.
Okay, thank you. So, hello everyone. Well, I'm going to present the work I'm doing with about this implementation of the learning to do the inversion of Stokes parameters. I'm doing this work along with the teachers and investigators Santiago Vargas and Sergei Sheliak, all along with the group of solar astrophysics of the National University of Colombia, and along with my partner Germain Nicolas Morales. And I'm presenting you for this Congress, this project. So, what am I going to present? I'm going to present a little bit of the relation within MHD and the Sun, some insights about the Stokes parameters, the neural networks we are using for the developing of this project, the results we've obtained until now, and the next steps we want to follow to improve these results. So first, the MHD. So we want to focus on the part of the data we obtain from the MHD, specifically about simulations from the MHD. So we can obtain all the information about plasma in the solar photosphere, specifically in that zone. So well, we have to take into account all the equations of the MHD. We all know about that. So what we can obtain from them, we can specifically obtain the state vector. So we obtain the magnetic field, the velocities field, the density, and the temperature. And these are the magnitudes that we are going to take into account for this project to train the neural networks we are going to use, along with the Stokes parameters. So we need information about the Stokes parameters because that's what we measure from the sun. So we want to obtain just the Stokes parameters and not do any solving of equations, of inversion equations, but just take them directly and through the neural networks, the model we use, so we can obtain directly the inversions, or inverse if we obtain the atmosphere parameters directly to the model, so we can obtain also the Stokes parameters from a simulation, so that we don't need to solve like the radiative transfer equations to obtain the Stokes parameters in those simulations. Okay, so one thing that we have to take into account from the Stokes parameters is that we obtain them as points. So we have low resolutions on the Stokes parameters usually, and also depends on the time that we take into account in the measurement. So usually we have just dots and low resolution. We usually do the fits with linear continuous plots, but that's not what we usually obtained. So from that's one issue we have to take into account. Initially, we are just taking the continuous lines from the plots, from the simulations, but that's eventually we are going to take lower resolutions for the project. But initially, we take just continuous plots. Well, a lot of points for the training. So, which neural networks are we using? Firstly, we are using a simple CNN, convolutional neural network, of 3 layers and 1 output. The output is the input of the layers is the values in an array, a 1D array. Depending on what we want, it can be the Stokes parameters alone or the magnitudes of the values of the magnitudes that I mentioned before along a height in the domain of the simulation. We have, I'm going to explain how the simulation is done later, but we take specifically pixels in X and Y in the surface and take all the values along the height as if it is a like kind of time series, but instead of time we have the height as the x-axis. Okay, so also we are going to use GANs. This is for generating the magnitudes of the that I mentioned before, specifically the atmospheric magnitudes, so that we can obtain the behavior of them for the photosphere in a domain instead of solving the MHD equations. So specifically, we are doing this with the magnetic field and generating for a domain of the simulation that we got from the MHD originally. So, what results have we got? Well, firstly, we are using data obtained from the MURAM code. This data was given thanks to the investigator Sergei Sheliak. He gave us this data along with also with pressure, along with the other magnitudes I mentioned before, also with the Stokes parameters. So we have magnetic field, velocity field, pressure, density, temperature, and the Stokes parameters. In each snapshot, we have 150 snapshots of 480 by 480 by 480. There are 3D snapshots. What we are training are in the convolutional neural network are height series of each pixel of the surface, and in the GAN parts of the domain. Like we take from the 480, we take 256, 256, and 256, so that it is less computational complicated. So first, we have what we predicted with the atmosphere parameters as inputs and the Stokes parameters as outputs in this convolutional simple neural network. This was done just with 10 epochs. As we can see of the results we obtained, the behavior are better. The information predicted is better behaved for the I and V parameters, but for the Q and U, the neural network couldn't really catch the real behavior of the Stokes parameters. So, but instead for the I and V, well, specifically for the I, we have that the shape it's really really close to the real behavior, and also the magnitude is really close. Like it can also take some of the absorption lines that we need to take into account when we are studying this kind of simulations, also the sun actually. And for the V plot, we have that the behavior of the ups and downs of the peaks and valleys in this plot are close to the real ones, well, to the ones that were produced by the simulations. So it's quite interesting that this was done just with 10 epochs. We are still producing more information about that and making some more training. Then we have these results. Here we changed the character of the Stokes parameters and the atmosphere parameters. So here we have as inputs the Stokes parameters and as outputs the atmosphere parameters. Why also we want to do this? Because we want to apply this to make the inversions to real images. So what we got from these simulations, these are all data from the MURAM simulation. That specifically for intergranular data, the plot is not, the prediction of the values are not that good. At least for velocity and magnetic field, the behavior and the behavior is very, very like far from the real behavior that we obtain from the simulation. But the density and the temperature behave a little bit better. Even with that, we can see that in the granular zones, the behavior is better predicted. So, and we are wondering why this is happening. Like, it's not about that it is imbalanced in quantity of data, because that's what we thought in principle. And actually, we balanced the quantity of data of intergranular and granular zones, taking as threshold a value of intensity. We balanced then, thank you. We balanced then that quantity of data. We thought that it would solve the problem, but it didn't, as you can see. So we are continuing and still figuring out what's happening here. Still with that, we got a mean squared error of the order of 10 to minus 3. So statistically, it is behaving well, but we have to study it about the physical behavior of the results that are being predicted. Also, this is the other result we've obtained with the using of GANs. My partner, Jeremy Nicholas, has obtained these magnetic field images generated for a 256 by 256 by 256 domain. These are generated by noise, as a GAN, essentially. But he also used for the generation of these images, not just statistical losses like mean squared error, but he also added the divergence to the loss and weighted them by 0.5 each of them. Also by we just choose these values of weights just by trying and seeing which ones were better. And this is the result we obtained. So which are the next steps we want to follow? For the convolutional neural network, we want to use, instead of optical depth, physical height, so that we do not have the granular forms, so that the model has to, let's say, think too much about these structures that are a lot more complicated than if we do it with optical depth. Because if we take optical depth, then we are going to obtain more uniform data for each slice, because we are doing a conversion, a mapping of all these granules to a plane of values. So it is going to be less computationally complicated. At least the height or the speed of the computational problem. Also, we want to separate in absorption lines in case we want to study just one absorption line with the instruments we have in real life. Have a low spectral resolution also for the Stokes parameters. We thought also about using neural units to use temporal evolutions. We've seen it has been done for fluid dynamics in cars. So we want to use it for MHD simulations in case it can work so that we do not need to solve the MHD numerical solutions, but just a model, a neural network model, so that we can obtain it faster. We wanted to add also the divergence of the magnetic field to the convolutional neural network, as we did in the GAN. And we want also to add the radiative transfer equations, so that we convert it to a physical informed neural network and obtain more accurate results. So that's it. These are our emails. Thank you very much.
We have time for questions and comments. Interesting talk as well. Over there.
Thank you for your talk. I have a couple of comments and questions. I don't know if someone has some other question, can interrupt me. So I'm curious, because what is the point of you to make the synthesis with the convolutional neural network or so? It's just speed, or because there are a couple of codes that they do the synthesis already in a fraction of a second. And since you have like 20% in the continuum, it's already a significant difference. So I missed that what the advantage of your method?
Of using the neural network.
Yes.
Well, the convolutional, it is, we also tried with a dense neural network. We were just trying to see which one could work, because there is not really a previous work about this, so we are just experimenting in this inversion with neural networks.
No, the inversions, there are a couple of methods already doing inversions with neural networks.
With neural networks.
Yes.
Well, at the moment we did it, we were just trying out what we could do a year and a half ago. So
because I think some of the things you are doing, you can already follow what people have done.
okay. Yeah.
Because something, can you please show me the your line profiles when you have I, Q, U, and V? So this one. This looks like an iron 1 line or something. I miss why you have height in pixels.
Why I have height in pixels? Well.
This is not wavelength.
Yeah, I just got it wrong. So sorry. Yeah, it's wavelength. It's wavelength.
So probably can compare a result. It's just a suggestion, because they are already codes who can synthesize those lines really fast, and you can use it as an input for your model to more accurately fit your lines.
Sorry, I didn't understand.
You can use those outputs because probably can solve you the issue from the Q and U.
Okay.
If you use Lightweaver or RH or even Desire, you can synthesize the lines properly and use them as a training set for your convolutional network. Actually, there are 2 papers or 3 papers that I know that they did this already.
Okay.
I can talk with you later on. Yeah.
Okay, thank you.
Any more questions or comments? Do we have anything online? Yes, I think we have Daniela. Could you please go ahead?
Yeah, so I want to emphasize that there are codes that are doing this pretty fast, at least for photospheric lines. So you may want to use that to check what you are doing. And also some suggestions, if you just want to continue playing, you can also consider scaling. So for what I'm seeing, you have the same, I don't know if scaling is the right word, the same scaling imposed for both for all the Stokes parameter. You may want to scale them to give more emphasis to the linear and circular polarization parameters, and that may help you a little bit. And also, no, that was all. Thank you.
Thank you.
Any
A
more
really
questions?
nice work.
Thank you.
Any more questions or comments? Let me ask you one. Could you get back to that 3-dimensional reconstruction of the magnetic field?
Yeah.
What do we see over there? I mean, are these just pixels or are they megameters? What are they exactly?
They are just pixels. Yeah.
The units of the axis, that is.
Yeah.
And then what do you see in color? Do we see the strength of the magnetic field, the amplitude?
Yeah.
But you do have all vector information in that particular reconstruction, right? So you have all 3 vector components.
In that particular reconstruction,
Or it's just the amplitude of the
it's
field?
just the amplitude of the Y.
Is
magnetic
this the
field.
only thing you can reconstruct, or you can reconstruct, because you mentioned about IQUV, so you could be able to reconstruct all the components of the field, is that right?
Yeah. That's what we are trying to do, but we are still experimenting with just one component.
That's fine. But if you have a situation like that, what you can do right away is to try to see whether your reconstruction has given you a valid magnetic field solution by checking the divergence of the field in 3 dimensions.
Yeah.
Have you done that?
Okay. Well, no, I'm sorry. Yeah. This part of the project is done by my partner, but I think it is the 3 components because he's taking into account the divergence. So there are the 3 components. Sorry.
Okay, so the divergence can be checked.
Yeah.
Have you done that?
Yeah. That this is included in the loss. It's included in the loss.
All right. So again, because we don't have any color map in there, I'm just trying to understand. what you have
It's a little
in
bit
3 dimensions, but nonetheless, this is very important.
Mm-hmm.
If you have 3-dimensional magnetic field information, any way you can get it. We have this big privilege of, being able to identify whether we have a valid magnetic field solution by checking the divergence. If the divergence does not work, if the divergence, and there are published metrics for checking the divergence,
Yeah.
if these do not work, then it's useless.
Yeah.
It's of no meaning to try to use this reconstruction. You have to have a good performance in the reproduction of the divergence-free solution in order to be able to go farther than that.
Okay.
So this is, I would consider it as important, keeping in mind.
Yeah. Okay.
Okay.
Thank you very much.
All right. Any more questions or comments? All right. Let us thank all the speakers again of this morning, and thank you, Juan. Very interesting.